Welcome! In this series of short videos, we will look at topics common to both the PowerBasic console and Windows compilers. Today we will look at thread-based searching. Today we're going to look at a practical demonstration of how you can use threads to speed up your search operations. We're going to be using some of the routines in the PB file handling routines library, so I've added this at the beginning of the program with an include statement. So the task for today is to create a large data file, and we will create a subset of that large data file, and we're going to search each record in the small data file to see if it exists in the large data file, and produce a third file of results that gives us a list of all the entries that exist in the small data file and which row number they have been found in. So I'm going to create three constants. One for the big data file, one for the small data file, and one for our results file. And in order to get some good timings on this, I'm going to create a large number of records in our big data file. So to give us a bit of flexibility in that, I'm setting the maximum number of records that are going to be created in a constant at the beginning of the application called max records. And we are also going to create two arrays, one to hold the big data file and one to hold this small data file. We're declaring these at the beginning of the program as global arrays. So our first task is to build the data files. So we'll create a function whose job it is to create each of these files. So here is our function that's going to create both the large and the small data files. We're going to randomly populate the large data file with a series of GUIDs. So we've defined a couple of handles to be used for creating these files. Using the constants we've defined earlier, we're going to open each of these files for output, a large file and a small file. And then we're going to run a simple for next loop for 1 to the maximum number of records, which we've currently got set at 200,000, and we're going to print out to the big file a GUID, which is randomly generated using this command that turns the GUID number into a human readable piece of text, and a simple print command to our big file to print out that piece of text and the time it was generated. So we will have two columns in this large file, a GUID column and a time column. And then we're going to use the random command to generate a subset of the large data file in the small data file. We're picking a number between 1 and 1,000, and if that number happens to equal 12, we will write a record out to the small data file. So the small data file will be considerably smaller than the large data file. And then after we've been through each record, we will then close off both of these data files. So this will create both the large and the small data files. So let's just compile that to make sure it compiles cleanly, which it does, and we will attempt to run it. So that has created 200,000 records. So if we have a look in our folder, we'll see there is the small data file containing 172 records, each row containing a GUID. In the large data file, we have 200,000 records, comprising of a GUID, a comma, and then the time in hours, minutes, and seconds. So now that we have each of these data files created, we don't have to run this at the beginning of the program each time it runs. The files are created, so we don't have to run it again. So we'll comment out the function that builds the files. So now that we know the files are created, our next task is to load these files into our arrays and do the comparison. So we will create a function to do the load and compare. And we'll call that function load and compare files. So in order to write this application initially so that it can be easily converted to be using thread handling, we're going to handle the searching in a series of sections. So we're going to create some new constants at the beginning of our code. We're going to create three new constants, one for the start section, one for the total number of sections, so we'll divide the work when we're doing it in a threaded manner into 10 sections. And we're going to create a constant to let the program know that we want to run it threaded or not. Since we're going to initially run it unthreaded, we'll comment out this constant for the moment. So having set this function up, we'll declare a local variable to keep track of the section that we're currently going to be doing, and we'll call that long section. We'll put a message out to the log to let us know that the data will first be loading. So we'll read the big data file into the array initially, and we'll use one of our common routines in the file handling library to do that. We'll use the read the file into an array. We're giving it two parameters, the location of the big data file and the array into which we wish to put that data file. And if this returns a true, then the big data file will be loaded. Otherwise, it will fail to load. So, on the assumption that our file has successfully loaded into the array, the next task would be to load the small data file. So we'll use exactly the same process for this. We will call the read the file into the array function once more with the two parameters, the name of the file to load, and the array into which the file is to be loaded. So at this point in the code, we've loaded both the big and the small arrays. As we want to know how long it takes to run this, because we want to compare the unthreaded version of the program with the threaded, we'll want to set up a timer. So we're going to create a quad variable called duration, and we're going to populate that with the value of the timer. This will give us a starting point for the operation, and at the end we will stop the timer and check to see what the difference is in seconds. So now we're going to do the comparison. So since we said we're going to run through this in 10 sections, we'll need a for next loop. From section equals 1 to the total number of the sections. And we're going to be calling a function called compare files that will compare the data within this section. Now we'll create that section in a moment, but the final task within this current function is to close off the timer and report how long it takes to run. We could do that quite simply by taking the current value of the duration equal to the current timer minus what's in the duration. And that will give us the number of seconds this process took to run. So let's create the compare files function now. So we're passing one parameter to this function, the number of the section to actually scan through. So we will throw a message out to the log just to indicate what the program's currently doing. And as we want to put the results of this out to a file, we will create our output file. For the output file, I'm appending to the end of the name of the output file the section we're doing. When we're running the program unthreaded, then in theory you could put all the results out to a single file. But as we're going to be running this later on as a threaded application, we want to give each thread its own file to write to. And then if you wish to append all the results files into one and resort them, this is easily done. So we're going to create some variables at the beginning of this function to handle what's happening inside it. We'll cover these as we come to them. So now that we've got the name of our output file, the next thing to do is to open the output file. And now we can start our comparison. Since we're comparing the data in the small file array with what's in the large file array, we can do a one-to-one match because the data in the small file array is just the GUID, where the information in the large file has two columns. It has the GUID and a time. So what I want to do initially is to work out the length of the data within the small data file. And we're lucky in this case because all the GUIDs are the same length, so I merely have to capture the length of the first one. Now we have to work out which row to start our comparison at, and this is a simple piece of arithmetic. Taking our block size to be the upper bounding of the number of records in the small data array divided by the total number of sections. And our start row is the section number minus 1 multiplied by the block size plus 1. So initially when we come in with section equal to 1, the row number we'll be starting at will be row number 1. And depending how big the small data file is, we will slice it up into 10 sections and process accordingly. The last section will have a variable number of records in it. as it won't be full block size. So we need to work out where the block ends. So if we're doing the last section, then the block end will be the upper bounding of the data in the small data array. If we're doing something other than the last section, then the size of each of these blocks will be equal to the start plus the block size minus 1. So having worked all that out, we can now, for each record in this particular section, do our comparison. So we're back to for next loops. So we're using our variable long R from the start row to the end row. And we're picking up and populating this small GUID with the value that's in the array. So the question is, does this GUID, this piece of data, exist in the big data array? Now there are a number of ways of actually doing that. We could do another subroutine that actually scans through using a for next loop. But PowerBasic supplies an array scan command, which is very powerful. And this is what we're going to use. This single line of code can be used to scan the entire array. It takes a number of parameters. We're giving it the array we want it to scan. We're telling it we want to scan the character positions from 1 to the length, and that's the length of a GUID. So we look at the first X number of characters, and we're looking to see if this equals the value we're giving it for this small GUID. And whatever it finds will be put into this long I variable. So if the value can be found, long I will be greater than 0. If the value cannot be found, then long I will be 0, which makes it very easy to determine if we've found something or not. So we can push out to our results file the details of the small GUID we've been searching for and the row number in the big array in which it has actually been found. And having done all that, we can close off the results file and we can say to our log that the scanning for matches has been completed in this particular section. So if we try compiling that now, it compiles cleanly. So let's run it and see what it finds. And there we have it complete. So we have a look in our results file. We'll see the results file as an entry for the GUID and the row number that it actually found the data in. So running our application for 200,000 records in an unthreaded mode will run very quickly. It takes a mere second to sweep through the entire thing. However, what if the number of records we were looking at was much larger than 200,000? Let's increase it to 2 million. And we will have to rebuild our files. So let's rebuild the files. And there we have much larger files. Our small data file has now 1937 records. Our large data file is considerably larger and will in fact have 2 million records. So if we comment out our build files and put back in our load and compare, recompile, and then we'll attempt to run this against the larger set of files. So let's see how long this one takes to run. Well, that took a little longer to run than the last one. It's now took 58 seconds to actually run this. So now that we have a baseline, about a minute to run through 2 million records, if we ran this as a threaded application, how much would it actually speed up? So how can we take our existing working application and turn it into something that operates using threads? Well, as you'll remember from the beginning of the code, we had a number of constants set up, and one of the constants we're now going to turn on is this run threaded constant. We're going to use the fact that this has now been defined as a switch to determine whether we run it threaded or non-threaded. So if we look first at our load and compare files function, we're going to have a section at the top of this function that will be testing the definition of the run threaded constant. This is going to create two arrays. The first array is to hold the thread handles. As we're going to run this in 10 separate threads, we need to keep track of each of those threads so we can determine when each thread has actually completed. And that's what this array is for. I've also created an optional one to keep track of the thread status. In the comparison section, when we're running unthreaded, we're using a for next loop. For each of these sections, it will run the compare files function, wait till that completes, and then run it for the next section. When we're running in threaded mode, we will run all 10 threads concurrently. So we're going to test the run threaded constant once more. And if that is defined, we will run our threaded section. If not, we will run the existing code. So when we're running threaded, we'll still need a for next loop. However, within that for next loop, we're going to use a thread create function. We're still going to be calling the compare files function, and it will still be passing the section parameter. When we call thread create, we get back the thread handle, and we're passing that into the array we've defined to hold the thread handles. So when running threaded, rather than running each of these calls to fun compare files one at a time, it will run them all concurrently. Since that's the case, it will shoot through running each of these very quickly. But you need to know when each of the threads, which is running quite independently, is actually finished. So by the time we get down to this line of code here, if we're running threaded, we need to work out, have all the threads actually finished, or are they still running? And to do that, we're going to create a new function called waitForThreads. It will take 3 parameters, the first being the total number of threads we have kicked off, in this case 10, a pointer to the array which holds the thread handles, and the number of the first thread, in this case number 1. And once we get past this line of code, we know all the processing is completed, and we can send a message out to the log to see how long the processing took. So let's create the waitForThreads function. The waitForThreads function is quite generic. You can use it in any of your applications where you're waiting for threads to finish. As I said, it takes the 3 parameters and will quite happily wait for all our threads to complete. So this function is quite adequate for what we're doing in this program. We're running a number of threads, and we want to know when all of the threads have actually completed. So the other thing we have to do is to make a change to the compare files function. Compare files at the moment is a standard unthreaded function. And just as we did before, we need to do a conditional compilation here to turn it into a threaded function. And that quite simply is testing, again, for this constant run threaded. If it is going to be a threaded program, then we will define the function with the word thread in front of it. And we will pass the section number as by val rather than by reference. Otherwise, we will call the fun compare files normally. So that should complete all the changes to our application to allow it to run in threaded mode. Let's try compiling that now. And it compiles quite cleanly. So let's clean out all the results from our last run. As you'll remember from the last time we ran this, it took 58 seconds to sweep through the 2 million records in our big file. In order to see what this is actually doing to the processor, I'm going to turn on a monitor that will let us monitor the CPU to see which CPUs are actually busy. As you'll see at the moment, each of the CPUs is very quiet. So let's try running the program now and see how that changes. It's now loading the data and now processing. As you will see, the processors are now a lot busier than they were before, as the load of doing all the calculations and searches is being spread across all the processors. And that's it completed. It is now completed in 10 threads, and it took a mere 12 seconds to run. So we're doing exactly the same processing in this program now as we were doing before. But instead of taking 58 seconds to process, it's now processing in 12. So if you have an application like this that's doing a repetitive piece of work in volume, then it's well worth designing your application so at some point in the future it can be easily converted to be running in threads. Hopefully you'll find this useful in your own applications, but that's it for today. Thank you for watching.